can see my slide?
Yes, everything perfect. Please start.
I'm sorry, I cannot share my slide, so I will start my presentation. So, I am PhD student in Tohoku University. I will talk about this topic. So, neodymium iron boron magnets are widely used in applications such as motors, but fluidity is one of the important properties of magnets, but it's actually less than 30% of the theoretically expected value. Neodymium iron boron magnets consist of main phases and grain boundary phases. Ideally, their magnetic grain are desirable to single crystals. Each grain magnetic are independent, and none of their non-magnetic grains. However, that is not actually the case. To understand the mechanism of cohesivity of neodymium iron boron magnet, it's important to know how magnetization reversal occurs in homogeneous microstructures. Here we have three conditions necessary to measure the magnetic domain of magnets. We can spatially measure the magnetic domain and microstructure at the same location. Second, the resolution of the magnetic domain is smaller than that of the main phases. The third is that it can be measured three-dimensionally. Until now, the magnetic domain structure of magnetic materials has been observed using methods that utilize the Kerr effect and spin SEM. However, we cannot observe the 3D arrangement of our magnetic domain of bulk magnet. There have also been attempts to obtain 3D magnetic domain information using neutron beams, which have high penetrating power, but it has low resolution. We have developed the measurement method meets these three necessary conditions. This is a method that combines X-ray tomography and 3D SEM. X-ray tomography can observe magnetic domain and neodymium distribution, and 3D SEM can observe microstructures. Information on the same position is obtained using the neodymium element distribution of each data. The result is the one on the right. This shows the three-dimensional magnetic domain and the microstructure that reproduce the hysteresis curve. As a result, various magnetic domain characteristics were observed. The first one is true to be the generation of magnetic domain reversal nuclei when 2.2 Tesla is applied. The second type is a particle that does not flip even when high magnetic field is applied. Also, these magnetic particles look like similar to the human eye. They behave in completely different ways. Next, the magnetic domain propagation has been observed in the three-dimensional detour like a snake or maze. This is one of the results that could be achieved with the conventional two-dimensional method. This way, we are able to obtain magnetic domain information of the magnet, which had previously only known through the three-dimensional observation of the inside magnet. So the content of this topic is to analyze patterns using similarity. The ultimate goal is to understand the magnetization reversal process inside the magnet. In the process up to that point, as explained earlier, I had achieved step 1. The next step is to perform the analysis. Now we must consider how to evaluate the process of magnetization reversal within inhomogeneous microstructure inside the bulk of the magnet. However, since no two microstructures are the same, comparison cannot be made. Therefore, we attempted an evaluation using informatics pattern recognition technology. I will explain the dataset used this time. So first, let's explain magnetic domains. The magnetic domain in this dataset are residual magnetic domain states after applying each magnetic field. Only the reversed magnetic after that, only the reversed magnetic domain are extracted three-dimensionally from those magnetic domains. Then by integrating them, I will show the razor point. So like that, extracted only reverse magnetic domain. After that, I did integration like that. The 3D for the microstructure, the SEM, I did perform the carry out SEM and SEM microstructure use baseline images. The size of obtained magnetic domain structure and microstructure is 10 by 15.5 by 15.5 15.5 nanometers. So in order to compare the data with the inhomogeneity, we decided to evaluate using structural similarity to the two on the left, this one, use the global features of the structure, of the information structure of the data, and the two on the right is the local features. First, mutual information is a measure of how much information in images shared. And the SSIM also evaluates similarity based on the brightness contrast structures. And the right side is the shift and the AtC-AtG evaluate local features. The shift can be expressed similarity with a high accuracy, and the AtC-AtG can be expressed a variety of the shapes of their structures. To evaluate the similarity, we first performed three-dimensional sampling, and randomly generated data is also available for comparison. This was very simple, dividing each structure into 3.3 nanometers cubes, like that. Then we calculated the similarity using brute force using the method I explained earlier. At this time, when divided by each at this time, when dividing by each structure, if the subscribe of R, this R are same, indicate the same spatial area. The calculated data is explained as the similarity matrix, like that. This is a result. The correlation was confirmed by similarity using a method. This is a result suggests that it's not impossible to evaluate the main. I can express the similarity of each structures. The correlation were more pronounced with the method using local features. Also, there are differences between AtC-AtG and the shift. We believe that this is because we believe that this is because the data contains many nonlinear structures which are related to correlations. Furthermore, since that similarity remains not low with the low random data, it's true that the characteristics of the structure can be grasped. So, as a demonstration, we will share the microstructure and the magnetic domain structures that have a high the structure with the high similarities. First of all, the cycler graph below shows this. The parts are arranged in cycle and connected by lines. So, for example, this batches, this batches, this batches, this, like that. And after that, the right circles, this one, the parts with the high similarity extracted from there. Among them, I cut out these yellow parts and displayed it on the right side. So I extracted from this triangle to these structures. These are structures that are not these are structures that are difficult to judge with the human eye, but these structures are evaluated as the ones with high similarity from the data information. So this is a summary of my research using similarity. Using similarity, we match the microstructure and magnetic domain structure, making evaluation possible. Next step is to investigate how the physical meaning is hidden. Thank you so much.
Thank you a lot for your reports. So now we have time for short questions. If you have, please raise your hand. Okay, I have a short question. So, do you have an idea how to correlate your features you extracted from CM images with actual microstructural features like triple junctions, grain boundaries, and so on?
Excuse me, sorry, can I
let me ask in a different way. You prepared some feature description of the data, right?
Mm-hmm.
And you would like to connect your actual microstructure with the main patterns. So far, you just used pixelized data, but can you use your current similarity matrices and representation? Can you link microstructural features now with actual features of the main pattern, like the main walls, something like that, and explain where they are located in a real microstructure?
We can correlate to the features correlate to local microstructure, but we now we can know idea to where microstructure for the information. Sorry.
I see. Thank you. It might be a very nice next